All right, so let's get back to our discussion about retransmission protocols. So we did an initial design that proved out to be flawed. And so now we have a great idea. We'll just get some sequence number into the protocol, and things will turn out to be good. So let's show that this is actually true, and let's now talk about one specific protocol called stop and wait. So stop and wait is actually very simple. So the idea is that the transmitter transmits a packet and then does nothing until either the timeout counter has expired, in which it transmits again, or until it receives an acknowledgement from the other end, and then it moves on. So it's a very conservative strategy in the sense that we only, or I don't know, very simple strategy that we transmit one frame and then wait until that has been acknowledged before we start to transmit the second frame, and wait until that has been acknowledged before we take the third frame. Okay, so in this case, the transmitter needs to maintain a state variable that keeps track of the sequence numbers of the transmitted frames. And it turns out now for stop and wait, since we're only transmitting one frame at a time, we don't need to enumerate that 0, 1, 2, 3, 4, etc. It's enough to enumerate them by 0 or 1. So for instance, if the first service data unit, number 0, then that gets sequence number 0. Service data unit 1 gets sequence number 1. Okay, the next one is service data unit 2, and now that gets sequence number 0. And just one, service data unit 3 gets then number 1. Okay, question?
Yeah, is this like the segmentation and reassembly method that we...
Yeah, no, it's not. It has really nothing to do with that. But so these, for doing segmentation and reassembly, you need to have sequence numbers for the fragments, right? So there are sequence numbers used there too, but that's not the purpose here. Okay, but the idea here is that we have service data unit 0, 1, 2, 3 that should be transmitted in order. But we transmit the first one, and it gets then sequence number 0. The second one gets sequence number 1. But once we have completed this transaction, we can go back and retransmit a frame with sequence number 0. And we can do that because we're only transmitting one frame at a time. Okay? And also, it's nice to keep the number of bits required to keep track of the sequence number as low as possible, right? Because this will create overhead in the transmitted frame. So 1 bit is the least we can hope for, which is the case here. So this sequence number then, as last, is then included in the header. The header could contain many other things also, but it's for sure included here. And then we have, of course, our friends, the check bits here, that keeps track of error detection. Now the receiver also maintains a state variable, and that state variable could have been, for instance, the sequence number of the last received frame, but that's not what we do. What we do instead is that we maintain a state variable that we call rnext. And to think about this, it's the sequence number of the frame, the next expected frame. Or another way to say rnext is the frame which is requested. Okay, the number of the frame that the receiver would like to see. So you can think of it as a request. Okay, so and then it's 0 if the last received frame had sequence number 1, and it's 1 if the last received frame had sequence number 0. So if this is S last here, we will see an example shortly to illustrate this. Okay, now, so what's happened now? We have two state variables, S last and rnext. Then the receiver receives a frame, say, and it will accept that if the sequence number in that frame, S last, is equal to R next. Okay. So if I'm the receiver, I get a frame, then I look at the sequence number. Is that the sequence number of the frame I would like to have? Then I accept it. If it's not, then I don't accept it. Okay. If a frame with correct sequence number is received, okay, I check the sequence number, I'm happy with this, then I send it up, okay, and then I need to send an acknowledgement to the transmitter, and in that acknowledgement I include the number of the frame I would like to see next time. Okay, and the frame I would like to see next time is the next frame sequence. Is S last plus 1 modulo 2. Okay, so basically what this means is that I need to update my state variable. So I take my state variable and I do modulo 2 addition with 1. So if I had 0, it becomes 1. If I had 1, it becomes 0, and so forth. And then I include that into the acknowledgement frame. So the acknowledgement frame contains my current state variable, that is, the sequence number of the frame I would like to see next. And then some check bits. Okay? Questions? Okay, so to recap, the sent frames or here includes a sequence number, which is 0, 1. The receiver checks the sequence number and is this equal to what I'm expecting? And what am I expecting? Well, I'm expecting R next. If S last is equal to R next, then things are good, and I deliver the frame, the service data unit. At the same time, I tell the transmitter, everything is fine, please send me the next frame, and the next frame is R next plus 1. Okay, and I include that in the acknowledgement. Okay, so crystal clear, I hope. Maybe not, so therefore we'll take an example. So under normal operation, again, frames can be lost, acts are never lost, and timeouts are longer than the turnaround time. It better work now, because it did before we had any sequence numbers. So we need to initiate start, before even transmitting the first frame, we need to agree upon a common start state. That is what is the value of S last, and what is the value of R next. We just need to do that in one consistent way. And one consistent way is to say that the receiver expects to see frame 0. Okay? And then we will see that means that the transmitter should have its S last equals 1. Because remember what S last means. It means semantically it's the sequence number of the last transmitted frame. Okay, there is no last transmitted frame here, so we'll just say there was number 1. Okay, so now we have a consistent start state, and things start now. So the service data unit 0 arrives. Now I'm the transmitter. I get service data unit 0. Okay, I transmit that. Okay, the first thing I do then is that I update my sequence number from 1 to 0. Put that into the frame, so the 0 here is the 0 here, right? And transmit that over the channel. And then start a timeout, of course. And then at the receiver checks the sequence number against R next, and it happens to be the same, right? So do a comparison between these two numbers. It's the same, and therefore it delivers it. And now it's time to send the acknowledgement. But before sending the acknowledgement, we go from, we just previously expected frame number 0, but now we have received frame number 0, and therefore now we expect to see frame number 1. So R next goes from 0 to 1 exactly at this point in time. And that is then included into the acknowledgement. So the acknowledgement then contains R next. So note here that here we go frame 0, the acknowledgement carries 1. Okay? Because the acknowledgement carries R next, the next one. But on the other hand, if I tell the transmitter, please send me frame number 1, that implicitly says that I just got frame number 0. Right? Okay, so this is a little bit different from what we saw a few slides earlier. Right? The numbering, the logic is the same, but the numbering is different. Okay, so what happens next is that service data unit number 1 arrives to the transmitter, and then the transmitter transmits that, or rather updates first its sequence number and transmits that over the channel. So this one is here, and then unfortunately this got lost. So what's going to save us now is the timeout. Timeout hits and it retransmits using the same sequence number, of course. And then this happens to be a timeout is started, and this happens to be received. The receiver then updates its state variable, right? It goes from 1 to 0 and transmits an acknowledgement with 0 in it. Okay? And then the second STDU comes here and so forth. Okay, so was the logic here clear? Okay, so what we have introduced now is a transitional state variables. So state variables change their values at specific points in time. So slast changed its value whenever a new frame is transmitted. Okay, a new frame, a new service data unit arrives, and before it's transmitted, we update the sequence number and then transmit that. At the receiving end, whenever we deliver a service data unit, we go from we update our R next. Okay, so these are the new things. So yeah, and then I forgot, but here we also update slast here, and then it's transmitted also. Okay, now we're done, I think. So now this was a normal operation, but this worked already previously, right? So let's see now what's going to happen when we lose X. That was one problem. Remember, when we lose X, we got duplicates. And then we will see what happens when we have too short of a timeout, which leads to both duplicates and lost frames. Okay, lost X. Okay, so this is solved now. So it's a busy slide, so let's go through this in some detail, slowly enough. So again, the start is the same, and we transmit frame with sequence number 0 over to the receiver, has the right sequence number, so this is delivered, and now the acknowledgements go over here, and it's lost. Okay, so what happens then is that the timeout expires, and it expires here, and that triggers a retransmission here, and the retransmission then has the same sequence number as we transmitted before. So what's going to happen now when this frame comes over to the receiver would first of all check for the errors and see there are no errors, and then check the sequence number and say, wait a minute, this sequence number is not what I wanted. I wanted 1. 1 is what I want. 0 is what I got. This is no good. So I throw away that frame because I know I already received that. As a matter of fact, I can suspect that my ACK got lost, right? So this frame here is never delivered. It's thrown away. Okay. Wrong sequence number, service data unit is ignored, and we retransmit the acknowledgement. Because we just received 0, but we wanted 1, so let's tell the transmitter again, hey, I don't want 0, I want 1. Okay? I want 1. Don't send me any zeros. I want 1. Okay? And then the transmitter here now gets the acknowledgement here and then figure out, okay, fine. Now I know for sure that the receiver has delivered service data unit 0. Okay. It just happens to happen here already, not here. But that's inconsequential, right? Okay, and then service data unit 1 may be transmitted here. Then, of course, we need to update the sequence number. It goes over the channel. And now everything is okay, right? Because 1 here is what we wanted. So we accept that. And then continue like this. Questions? Clear? Okay. So that problem is solved. How about timeouts? Okay, so again, it's a little bit complicated, but let's go through it. Start is the same. We deliver the service data unit 0 at this point in time, and then transmit a acknowledgement here. The problem is that at the transmitter side, the transmitter is a little bit nervous, and at this point in time assumes that something wrong has happened to the frame because it has not received the ACK yet, and retransmits the same packet. So a retransmission event is triggered here due to that the timeout happened. Okay, at the receiving end, we inspect the sequence number of the received frame, checks that towards what we expected. If they are not the same, we discard the frame. Okay, so we ignore the service data unit here. So this one is never delivered. But okay. But we transmit the acknowledgement again here because we request number 1 again. The receiver here has no idea what has happened, right? It basically assumes that the first acknowledgement it sent was lost, maybe. But it really doesn't care, right? I mean, it just informs the transmitter again that it wants 1, not 0, what it just received. Okay? The transmitter is happy now because it receives an acknowledgement within the timeout. Okay? So at this point in time, the transmitter knows that service data unit with sequence number 0 has been delivered. Okay, and then it can go on to transmit the next one whenever that arrives. Okay, when that arrives, the whole process is repeated. Okay, so there will be a lot of unnecessary retransmissions here, but the logic of the protocol or the service still is functional in that we deliver packets only error-free and without duplication and in order. Okay, questions? Yes?
Would there ever be any need of timeout in the receiver?
Okay, so the question is, would there be a need for a timeout when we transmit the acknowledgements back here? I don't see that needed for the logic here. And also the problem with that is that even if we had a timeout here and transmitted this again, we can transmit a lot of these acknowledgements unnecessarily, because what triggers everything is when these arrive, and we don't know when they arrive. Right? They arrive now, and maybe there is 2 minutes until the next one, and then the receiver starts to transmit AX completely unnecessarily. So, to my knowledge, timeouts are not used in the reverse link here, or the ACK for the AX here. That's a good question. Anything else? Okay. So now let's go through the logic here a little bit, or wrap everything up. So the stop and wait ARQ transmitter follows this logic. It has a state variable or sequence number, and it needs to be initiated. And let's assume that it's initiated to 1 here, which means that R next needs to be 0 at the receiver. We could select some other starting state, but this one is consistent. So let's go with that. Okay, so S last equal 1, that means that the first actually transmitted frame will have sequence number 0. And we see that because then at power up, we start with this, S last equals 1, and then we enter into the ready state. And when we're in the ready state, we wait for service data units. If no service data units is arriving, we do nothing, right? We just wait until this happens. Once we got a fresh service data unit, what we do is to update the sequence number. So whatever we had before, we add 1 to it. So if it was 1, 1 plus 1 is 0. So 0 is the first sequence number of the first frame that's transmitted. We start a timer, we transmit the frame with sequence number S last, and then we go to the wait state. And in the wait state, we block the upper layer. Okay? So if I'm the transmitter and just transmitted a service data unit, I just, tell the layer above me, I'm busy, don't disturb me. I won't accept any more service data units from you until I have made sure that this one has been delivered. Okay? So I block the upper layer. And then if the timer expires, then I reset the timer and retransmits the frame. If I receive an acknowledgement frame, I receive an acknowledgement frame supposedly from the receiver, I don't know. The first thing I do is to check for errors. And if errors are detected, or if there are no errors but the wrong sequence number is in the ACK, then I ignore it. Okay. Again, I don't trust frames with the errors in it. And the logic says also that if I get the wrong sequence number, I should not care about that. Then that acknowledgement is bogus somehow. So, and if no errors are detected and the correct sequence number is in the frame, that is that R next is equal to S last plus 1, because this is what I expect. If I just transmitted frame 0, I expect the acknowledgement to ask for frame number 1 to be transmitted next. Then everything is okay, and then I go back to the ready state. And then I can accept now a new service data unit from above. Okay, so this is the transmitter logic. Questions? Yes?
What if the acknowledgement is wrong?
Wrong in what sense?
If it's, let's say, it gives you a 1 when it shouldn't be 1, for example.
Okay, so if the acknowledgement frame is wrong, there are two things that could cause it to be wrong. Either there are transmission errors, bit errors in the transmission, and then hopefully this is detected and then it's discarded. But if the error is not detected, but the sequence number is wrong, I don't know, something bad has happened. I don't know what, but I'll just ignore it. And we will see later on that this is the right choice to do, because then we remain the integrity of the protocol. Okay, the right thing to do in that case is simply to ignore it.
I mean, for example, if the receiver sends an acknowledgement for 1,
Yeah.
and the next one should be 1 because that's what it sent.
Yeah.
But the receiver wants to get 0. So it's, for some reason, the transmitter gets a wrong acknowledgement.
Okay, so let's keep track of transmitter and receiver here so I understand it. So you're concerned with that the transmitter gets an acknowledgement with the wrong sequence number?
Yes.
Yeah. So the good thing, what it should do then is just simply to ignore it. And what's going to happen then is that it will trigger a retransmission at this point. So, for instance, if this now happens to be 0, okay, the transmitter knows it just transmitted 0, and now the transmitter asks for 0 again, well, then then that's not what I expected it to do, but let's just ignore it. And what's going to happen then is that when we hit the timeout here, it will do a retransmission. Okay, it's not needed, but it will not destroy anything. So the safe thing for the transmitter to do when it receives an acknowledgement that it either doesn't expect or has errors in it is just to ignore it, because then it knows the whole thing will recover. Because it would then eventually retransmit what it just retransmitted, which is not maybe not necessary, but it won't hurt things. Okay. Right, so let's look at the receiver logic. And the receiver logic is that we need to initiate it, and it needs to be consistent with the first frame which is transmitted. So it should be R next equal to 0. If S last is equal to 1, then R next needs to be 0. Okay. So then it goes into the ready state and awaits the arrival of a new frame. Okay. When a frame arrives, it checks for errors. If no errors are detected, it extracts the sequence number from the received frame. If the sequence number is what it expects to see, that is that S last is equal to R next, then it's the right frame. Then it delivers the service data unit to the upper layer, updates its sequence number, because then it would like to see the next frame. So R next is equal to R next plus 1. And then sends an acknowledgement with this sequence number to the transmitter. Okay. If the sequence number is not the expected one, so S last is not equal to R next, then we throw away the frame and retransmit the acknowledgement with R next. Okay, so we inform the transmitter that I would like to see R next. Okay. If errors are detected in the frame, throw it away. Nothing, things could go wrong if we are not doing this. So let's be safe and throw it away. Questions on this logic? Does it make sense to you? Okay. So this is what you need to implement for the project, right? Stop and wait. To really show that the protocol is correct, that it delivers in order error-free frames. That's what it needs to do. We can look at how these states change over time and see that there is only one path possible here, and that path generates implements this error-free in the right order transmission of service data units. Okay, so to see this, we studied the global state. Okay, so the global state of this, we have a transmitter and receiver. So the transmitter has S last, and the receiver have R next. If we put them together, we have the global state. So the global state is S last and R next. And what does that mean? It means that frame S last is the last one that has been sent, and frame R next is expected by the receiver, sorry. So this is the receiver, and this is the transmitter. Okay, and we need to, okay, so what are the possible states? Well, it's 0, 0, 0, 1, 1, 0, and 1, 1. These are the possibilities, right? There are no other possibilities because S last and R next are binary. Okay, so we need to start somewhere. And remember that we initiated S last to be 1 and R next to be 0. And the first frame causes S last to go from 1 to 0. Okay, so let's assume that we are in this state, meaning that we have transmitted 0 and the receiver expects to see 0. Okay. what can happen then? Two things can happen. That the frame 0, which we have just transmitted, does not arrive error-free. Okay? As long as that happens, then R next will never be updated. It will remain to be 0. There are ACKs sendings back and forth and so forth. But for sure, as long as frame 0 is not arriving error-free, then R next will never change. The transmitter will never transmit frame number 1 because it's still trying to transmit frame number 0. Okay? So it would just go around here, round here, until this following event happens, that frame 0 arrives error-free. If it does, then the receiver updates its state. So it goes from R next, which was 0, and then it becomes 1. Okay? So we transition from state 0 to state 1 at the receiver. The transmitter state is not changing with this event because this is a receive event. Okay, the receiver also transmits frame 0 acknowledgement. So it acknowledges that it has received frame 0. And it does that by asking for frame number 1. Okay. So now we are in this state, the 0-1 state. So what's going to happen here is that we just transmitted frame 0 ACK, and maybe it's not arriving error-free. Okay. And then we just keep on going here until, first of all, the transmitter state will never change until it receives a new error-free frame with the right sequence number. So this one would remain the same. The transmitter state will never change until it receives an ACK with the right sequence number. Okay, so nothing will happen until frame 0 ACK arrives error-free, arrives at the transmitter side. And then eventually the transmitter has a new SDU to transmit, and then it transmits frames number 1. Actually updates then before transmission, it updates its transmission state because then this is the last frame transmitted. So we go from 0 to 1 here. The receiver state does not change. Okay, so now we're down here, and the transition from here to here is basically the mirror of what's going on in the upper side. So what happens then is that if frame number 1 does not arrive error-free, we just spin around here. Whenever frame number 1 arrives error-free, then the receiver state updates from 1 to 0. And we transmit frame number 1 ACK. If frame number 1 ACK is not received error-free, it spins around in this state, and then we eventually go back to this state whenever frame 1 ACK arrives error-free. Okay, and I claim that this is all the transitions which are possible in this state, global state. No other transitions are possible. We cannot go across here or anything like this. This is the only thing that happens. And then if we look at here, the important part is here and here. And we see that we go around here eventually. We go around here, round and round and round. These are the only, we can stop here for a while, but then we continue and maybe stop here, but we continue round, round, round here. So that means that we receive frame 0, receive frame 1, receive frame 0, receive frame 1, and so forth. Keep on going like this. And this is the only possible way, right? Except that we can remain in this state for a long time, possibly, right? But we can never do duplicates, and we can never transmit or deliver service data units out of order. It's frame 0, frame 1, frame 0, frame 1, frame 0, frame 1, error-free. Okay, that's the only possible way forward. Questions? Okay. So what we have done now is that we have implemented our first retransmission protocol, the stop and wait. It's the simplest of all the protocols that we will talk about in this course. But it does something very powerful, right? it ensures that we can transmit packets error-free over a network where there are errors in it. Not only error-free, but also to avoid duplication and avoid reordering of frames. Now, if we want to do something more efficient, and you will see later on why we would like to do this, the efficiency of this stop and wait protocol is not super good when there are long transmission times. So that is, when I transmit the packet, it takes a long time before it's actually at the receiving end, and then I have to wait for the acknowledgement to come back. So if there is a long long delays in the network, I spend most of my time waiting. Waiting for an ACK or waiting for a received frame. So can we do better? Well, one way to do better at the transmitter side is not to wait for an acknowledgement, but rather to transmit, be a little bit optimistic, right? And transmit several frames if we have several frames to transmit, why not just transmit them and keep track of the acknowledgements as we get them back, right? Okay, so and the method to do that, or the standard method to do that, is to use a sliding window transmitter. And what it does is that, remember, what we would like to do is to provide a service from layer n to layer n+1. Okay, so layer n+1 has a number of service data units that it needs to transmit. 0, 1, 2, 3, 4, etc. Service data unit from 0 to 4 have already been pushed down to the lower layer. Okay, it still has frames up here that needs to be, or service data units that needs to be transmitted here. Layer n has a buffer. This is the purple one, is the buffer, and the buffer here can it's sometimes called, it's actually called the send window, but it's a buffer. And that buffer can buffer WS frames. In this case, WS is 1, 2, 3, 4, 5, 6. Happens to be 6 in this example, right? In this send window, here we put SDUs that we have transmitted, but not yet gotten acknowledgements for. So these are the service data units that somehow are in the process of being transmitted, or delivered rather. They have been transmitted from the transmitter, but the transmitter is not sure that these have been delivered. The previous service data units it has received acknowledgements for. So the green ones here, the transmitter knows have been received, and it does not need to store them anymore. So these are our previous frames that already been transmitted and acknowledged. Okay, delivered. Okay, so in this buffer here, we maintain now two state variables. One which is slast, and this has now the meaning of being the oldest frame which still has not been acknowledged. Okay, so this is the oldest frame that I'm not sure yet has been delivered yet. And then we have sRecent, which is the most recently sent frame, which is still not acknowledged. Okay, and then it happens to be a little bit of empty space here. And as long as there is empty space here, I can accept new service data units from above. When there is no empty space here, I need to block the upper layer because I don't have space in my buffer. Okay. So the logic here is that we accept service data units from the layer above as long as there is space in the send window. Whenever we get a new service data unit here, so for instance when we get the fifth one down here, we update sRecent and move that to the right. Okay, so we increment sRecent and then transmit a frame with the correct sequence number. Okay, and whenever we receive an acknowledgement, suppose we receive an acknowledgement here for service data unit number 2, what we can do then is that we can, the transmitter then does not need to store this because we know that this has been delivered. So this is deleted out of the buffer, and then we free up some space to the right. Another way to say that is that we take the window and we slide it to the right with 1 point, 1 item. So this sliding here is that we take the boundary now here and we make this green, and then we add a purple one here. So this is called sliding the window, which is essentially being that we push out the frame that we know has already been received. Okay. So slide the window to the right when leftmost frames are acknowledged, and then freeing up space in the send window, which means that I can now take another service data unit from above. And then, as before, we retransmit frames when their timers expires. So for each transmission, there is an individual timer, typically. Questions? Okay. So if we have one of these sliding window transmitters, we can transmit several frames at once, and we keep them in the send window until they've been acknowledged. If they have been acknowledged, we discard that, free up that buffer space, and we can then accept new service data units from the layer above. So these sliding window transmitters are used in many protocols. One which is called Go Back N, which we will look at momentarily, and one which is called selective repeat. Okay, so let's go back N. It has a particular type of receiver, which is very similar to, it's basically the stop and wait receiver. So what we do then is that we maintain a state variable, rNext. Okay, so this is the sequence number of the next frame which is expected. We have a receive window which is 1 frame long. So this is a buffer space in the receiver. These service data units are those who have already been delivered and acknowledged to the transmitter. So the receiver waits, as usual, until a new frame arrives, checks it for errors, and if no errors are detected, and if there is a correct sequence number, then we deliver the service data unit to the upper layer, increment rNext, and send an acknowledgement. If there is an incorrect sequence number, we can do two things. There are 2 variations of this protocol. Actually, I should say this also. There are many variations to these protocols, but so one has to be a little bit careful when reading in different books. Go Back N is in different. Stop and wait is basically the same in every book, right? Because it's so simple. But Go Back N could be a little bit different from book to book. Okay, but anyways, there are 2 variations here, 2 main variations, and one is that we either don't send an ACK or we retransmit the ACK with the sequence number that we would like to have. We just assume that this is the logic that we use now. Okay, if errors are detected, we do as usual, we just throw away the frame, and we don't send any ACK. Okay. Now, one thing that we note here is that when we send an ACK with some sequence number here, rNext, it implicitly acknowledges all frames which have sequence numbers less than rNext. Okay, and this includes some robustness against lost ACKs. And we will see that this is actually useful in a second. So let's talk about Go Back N here. So this is a little bit of a simplified timing diagram, but it's quite dense. So let's go through it a little bit. So TF here is the time to transmit 1 frame. Okay, so if we're transmitter, we can transmit 1 frame here, and then actually it would take TF seconds before we can transmit the next frame, and we can do that here, and then we have to wait TF seconds before we can transmit the next frame. So here the transmitter is really pushing out frames as quickly as possibly can do, right? So we have sequence numbers here. So the first frame here, I don't know what color this is. Let's call it blue, even if it's not blue. The blue frame comes here to the receiver, and then the receiver would like to see, the next frame it would like to see is the purple one. So it sends an acknowledgement back with the purple sequence number. At the same time, the purple frame is actually in transit, and it arrives here, and then the transmitter would like to see the green one, so it transmits an acknowledgement back to the receiver saying, I'd like to see the green frame. The green frame is actually already in transmission. Okay, and when the green frame comes here, it says, okay, I'd like to see the orange one, and the orange one is actually in transmission. But here the orange ones get lost. Okay, so what happens then? Well, the logic of the receiver is then that the next frame that comes, which happens to be the blue one, has the wrong sequence number. Because it was expecting the orange one, it got the blue. I don't want the blue, I want the orange one. So what do? Well, I do nothing, because I know that the protocol will recover eventually. So the next frame I get is the purple one. I still don't want the purple one, I want the orange one, but I do nothing. Here, the timeout of the orange one hits here. Okay? And since the orange one has not been acknowledged at this time, it's retransmitted here. And now the receiver is happy because he wanted the orange one. So then it can say, okay, give me the blue one, and then the blue one comes. Give me the purple one. The purple one actually is on its way, and it arrives here. We see that those frames here, which are dashed, are all retransmissions, right? They have already been transmitted once, but they have not been acknowledged by the receiver. So that's why they are retransmitted. And we see also that a single frame here triggers not only the retransmission of the frame that got lost, but also its neighbors. As a matter of fact, capital N of those will be retransmitted. That's a consequence of this protocol, and this is why it's called go back N. At this point, anyways. And what is N here? Well, it has to do with the timeout and how many frames we happen to be able to transmit during the timeout. Because the transmitter does not understand that something has gone wrong until the timeout hits. So N, the number of frames that are retransmitted, is the timeout divided by the time it takes to transmit a frame. Okay. So this is go back N, and it's a vast improvement of stop and wait, especially for those channels where these events, the error events, are rare. And when the time it takes to transmit one frame from transmit to the receiver is fairly long. We will see this in equations a little bit later. Okay, I think we end here. Sorry for taking. You should cut me off earlier.